This is one of the most expensive and complex machines ever built by humankind. Constructing it costs more than $3 billion and takes over 7 years to complete. It can dive to depths of more than 3,000 feet, remain submerged for months without surfacing, and launch missiles capable of altering the course of war. But how exactly is a nuclear submarine? An engineering masterpiece that remains nearly invisible even to the most advanced radars, built. Right now, you are about to witness this incredible process. A nuclear submarine is a highly sophisticated engineering marvel, and its creation begins long before the first sheet of metal ever touches the manufacturing tools. The initial designs are developed using advanced computer modeling software. At this stage, several critical parameters are considered, including hull dimensions and shape, power systems, weaponry, and noise reduction technologies. The length can range from 300 to 550 feet, directly impacting the submarine's diving depth based on its class. The most advanced submarines can descend to depths of 2,000 or even 2,500 feet, while some experimental models can go beyond 3,000 feet. Based on these initial designs, physical models of the submarine are constructed and tested in water tunnels. This allows engineers to analyze how the hull shape affects maneuverability, water resistance, and noise levels. Meanwhile, computer simulations help predict the submarine's behavior underwater at different speeds and during various maneuvers. Once all simulations confirm the calculations, the blueprints are sent to production. This is where theory turns into practice. Building nuclear submarines requires special materials capable of withstanding extreme pressure at great depths while providing corrosion resistance. Typically, high-grade steel or titanium alloys are used. Steel is more cost-effective and easier to manufacture, as it can endure high pressure and impacts. Titanium, on the other hand, offers superior strength, corrosion resistance, and non-magnetic properties, which reduce the risk of detection. However, titanium is more challenging to process and weld, as its melting point is significantly higher, approximately 3,034 degrees Fahrenheit compared to steel's 2,500 degrees Fahrenheit. Before construction begins, all metal sheets undergo heat treatment, which involves heating, cooling, and applying special anti-corrosion coatings. The hull of a modern submarine is assembled from modular sections, simplifying the construction process. Metal sheets are cut with massive laser and plasma cutters, ensuring precision down to the millimeter. Each sheet is then shaped using hydraulic presses to achieve the desired curvature. Some parts of the hull feature spherical or cylindrical structures. The sections are assembled separately. These are massive rings, or compartments, that will be joined in the final stage. This modular approach allows different sections of the submarine to be worked on simultaneously, accelerating the overall construction timeline. Once all components are ready, the most critical phase begins: welding the hull. Welded seams must be exceptionally strong, as even a microscopic crack could lead to catastrophe at great depths. To meet all safety standards, automated electron beam welding is used, producing perfectly uniform seams. Additionally, every weld is inspected using ultrasonic scanners and X-rays. Most nuclear submarines feature a double hull design. The strong inner hull withstands deep-sea pressure, while the outer hull provides a streamlined shape, improving hydrodynamics and reducing detectability. Ballast tanks are often located between these hulls, allowing for buoyancy control. To keep the submarine as stealthy as possible, anti-sonar coatings are applied. These include noise-dampening polymer tiles that absorb sound waves, microporous composite materials that minimize the submarine's acoustic signature, and noise-reducing coatings for the propellers and power systems. Once all sections are ready, they are connected. Gigantic cranes transport the compartments into specialized docks, where they are bolted and welded together. The completed hull is then tested for air tightness by filling it with compressed air and checking for leaks. A structural integrity test is also conducted in a hydrostatic pressure chamber, simulating real deep-sea conditions. Once the submarine's hull is assembled and its strength verified, it is time to install its most crucial component, the nuclear reactor. This is the heart of the submarine, allowing it to stay submerged for months, or in some cases, even years. A nuclear reactor is more than just a machine. It is an entire energy system consisting of various auxiliary components that occupy a significant portion of the submarine. Modern nuclear submarines use reactors that function by heating water to generate steam. The nuclear fuel, typically enriched uranium-235 or uranium-238, is placed inside the reactor's core. As nuclear reactions occur, heat is produced, which then heats water in a closed-loop system. The resulting steam drives turbines that generate electricity and power the propeller. The reactor is transported in protective containers and installed using cranes through a designated hatch on the upper part of the hull. It is placed within a specialized compartment in the submarine's core, surrounded by radiation-blocking materials. This compartment is also equipped with emergency cooling systems and reinforced safety barriers. The reactor is mounted on a shock-absorbing platform that minimizes vibrations and impacts during submarine movement. Next, heat exchangers and steam generators are installed to ensure efficient coolant circulation, followed by the installation of turbines and electric generators, critical components for the submarine's overall operation. Finally, the compartment is sealed with multi-layered lead and composite panels to minimize radiation exposure to the crew. To ensure functionality, an initial test ignition of the reactor is performed. During this test, power levels are gradually increased, radiation levels in all compartments are measured, and cooling systems are tested under maximum loads. With the reactor in place, the submarine is still far from operational. At this point, it consists of empty corridors and compartments, so the next step involves installing control systems, life support mechanisms, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull, enabling the detection of enemy vessels and underwater terrain mapping. The onboard computer system and automated combat control stations are integrated, ensuring precise maneuvering capabilities. Weapon systems are also installed. Torpedo tubes are positioned at the front, equipped with automated reload mechanisms for rapid firing. Strategic submarines are fitted with missile launch silos located in the central hull. Each silo is equipped with hydraulic locks and pressure control systems, allowing for missile launches at extreme depths. Considering that the crew can remain submerged for months without surfacing, nuclear submarines must be self-sufficient. They are equipped with oxygen generators, carbon dioxide removal systems, heating and ventilation mechanisms, and water reserves. Ever seen those tiny capsule hotels? Well, submarines have something very similar: sleeping capsules. They also feature dining areas stocked with provisions and a command center filled with control panels, maps, and communication devices. After the living quarters are fully equipped, the submarine is almost ready for deployment. But the most thrilling phase remains: a series of rigorous tests to prove that it can withstand immense pressure, stay undetectable, maneuver in extreme conditions, and perform combat missions. These tests can last anywhere from 6 months to 2 years, and include both factory trials and combat training for the crew. The submarine undergoes another airtightness test, followed by assessments of its electrical and navigation systems, and a final reactor ignition. For the first time, the submarine leaves the shipyard and enters open waters. Stabilizers, hydraulic cylinders, and steering mechanisms are tested. Sharp turns, dives, emergency maneuvers, and maximum speed tests, typically 25 or 35 knots, are performed. The submarine then submerges to periscope depth, about 65 feet, to evaluate stability. At greater depths, ballast tanks are tested under load, and the submarine is gradually lowered to its maximum allowable depth, usually around 2,000 feet, depending on its class. Reactor performance under maximum load is also assessed. Once the submarine has proven its seaworthiness, combat systems are tested. Initial shots are fired using training torpedoes without warheads. Strategic submarines conduct the launch of a single ballistic missile, typically following a launch-dive-airburst trajectory. Tactical submarines perform test launches of Tomahawk missiles or similar weapons. The submarine also enters an area with hydroacoustic sensors, where specialists measure noise levels at various speeds and evaluate the effectiveness of its sound-absorbing rubber coating. Finally, the submarine undergoes a simulated combat mission, during which the crew must demonstrate full operational readiness. Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often, my dad rarely had time off, but when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamond's unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectron volts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes. Imagine a place where time seems to stand still. Deep underground, nestled in the mountains of Pakistan, lies one of the most remarkable mines in the world, the Qura Salt Mine. This place is more than just a mine. It is the largest producer of pink Himalayan salt, renowned for its purity and rich mineral content. The Qura mine is an expansive underground complex made up of numerous tunnels and chambers where salt extraction continues without interruption. From the very beginning of my journey, I felt as though I had entered another world. The entrance to the mine looks like a gateway to an ancient, almost magical realm. Here, they extract some of the purest salt on Earth, the famous pink Himalayan salt. Let's walk through the old tunnels together and discover how this remarkable process takes place. The walls of the mine are lined with layers of pink salt, and each layer tells its own story, preserving the memory of millions of years of geological activity. The sense of descending deep into the earth is heightened by the near silence, broken only by the echo of footsteps and the hum of machinery at work. Salt extraction at the Qura mine is carried out using traditional methods that have changed very little over the past 200 years. It all begins with drilling holes into the salt walls. Miners use powerful drilling machines to bore holes into the rock. Drilling is a crucial and delicate step, as the precise placement of the holes determines the efficiency of the entire process that follows. Once the holes are ready, the workers carefully insert gunpowder capsules into them and connect them with wires. This must be done with extreme precision to ensure that the blast does not compromise the structure of the mine or create safety hazards. For each borehole, they use 4 capsules. Once all the charges are set, the blast occurs, separating large chunks of salt from the wall. This process requires great accuracy and skill to avoid damaging the surrounding salt layers and to maintain safe working conditions. After the explosion, the cleanup phase begins, which is also a labor-intensive task. Workers use special equipment and manual labor to carefully sift through the debris, selecting the best pieces of salt. This phase can take several hours, and sometimes an entire day, depending on the volume of salt being extracted. After the explosion, workers use excavators to clear away the large chunks of salt. The excavators lift these blocks onto special carts, which then transport the salt to the sorting area. Here, the highest quality pieces are carefully selected by hand. This process is time-consuming and requires great attention to detail to ensure that only the best salt makes it to production. The miners break the salt into smaller pieces, which are then meticulously sorted for further processing. It is remarkable how crucial the human element is in this operation. Only experienced workers can determine which pieces of salt are suitable for refining. They assess the color, clarity, and texture of the salt to choose the best material. Working in the mine is not only physically demanding, but also dangerous. Humidity and temperature in the mine often fluctuate, and the salt can become slippery. Miners must remain vigilant at all times to avoid injury. Despite the challenges, they take great pride in their work, knowing that their efforts benefit millions of people around the world. Once the salt has been brought to the surface, The next phase of processing begins. First, the salt is sorted by size and color, with only the purest and most visually appealing pieces moving forward. Then, the salt goes through a washing stage. Large chunks are submerged in huge vats of water, where they are thoroughly washed to remove any impurities. This step is crucial to maintaining the product's high quality and ensuring its cleanliness. The washing process is repeated several times until only the purest salt crystals remain. Each cycle is carefully monitored to ensure that every grain meets strict quality standards. Washing is one of the most labor-intensive stages, as the salt must then go through the drying process. First, the salt is pressed to remove excess water, and then it is placed in special drying chambers where it slowly dries. This method helps preserve the salt's natural structure and unique properties. It's essential that the salt remains as natural as possible, and the washing process, free of chemical additives, guarantees this. One of the most fascinating stages of salt processing is the creation of Himalayan salt lamps. Craftsmen carefully shape large chunks of salt by hand, giving them a variety of forms. Each piece is given a unique shape. Some lamps retain a rough, natural look, while others are crafted into smooth spheres or pyramids. After shaping, the salt is washed again to remove any remaining impurities. Then, the craftsmen insert electrical components, transforming the salt block into a lamp that emits a soft, warm glow. The process of making salt lamps begins with selecting the right chunk of salt. Using specialized tools, artisans shape the piece, a process that can take several hours, since each salt block is unique and requires an individualized approach. Once the shape is finalized, a hole is drilled into the salt to accommodate a light bulb, and the electrical components are installed. Every lamp undergoes a quality check to ensure it is safe and built to last. In addition to lamps, the factory also produces other salt items, such as bowls and pyramids. These pieces are handmade, making each one a unique work of art. The lamps come in various sizes, ranging from small to very large, with some weighing up to 20 or 30 pounds. These creations serve not only as beautiful interior decorations, but also as sources of comfort and warmth in the home. Each product is subject to strict quality control, and only those that meet high standards are made available for sale. After the salt goes through the stages of sorting and washing, it is ground into fine crystals. The salt is then sent to the purification stage, which involves several additional steps. The crystals are passed through large rotating drums, where they are heated to remove all moisture, making them dry and ready for use in the kitchen. This process is crucial for preserving the flavor and quality of the salt. Each step of the processing is carefully designed to ensure the final product is of the highest quality. After drying, the salt undergoes a grinding process. Special mills are used to crush the larger crystals into smaller ones. The salt is then sifted to separate any particles that are too large. These larger particles are sent back for further grinding to achieve a uniform consistency. This step is important to ensure the salt is convenient for kitchen use and has crystals of a consistent size. Once the grinding is complete, the salt is checked for impurities. It is passed through magnetic separators to remove any metal particles and through optical sensors to detect other contaminants. Only after the salt has passed all inspections is it sent for packaging. After all the processing stages, the salt is ready for packaging. First, it is packed into large bags for bulk distribution, and then it is portioned into jars or packets for consumers. Each packet retains the salt's beautiful pink hue, a sign of its natural origin and rich mineral content. Workers manually inspect each package to ensure everything is done correctly, and the product quality remains top-notch. It's a meticulous job, but this careful inspection ensures consumers receive a high-quality product. At the packaging stage, modern equipment is used to speed up the process and minimize direct contact with the salt, which is essential for maintaining its purity. The salt is packaged in various forms, from small plastic jars to large bags for restaurants and food industry businesses. After packaging, each batch of salt is labeled with the production date and expiration date, so consumers can trust the quality and freshness of the product. It's said that Himalayan salt lamps help purify the air and reduce radiation from electronic devices. While there is little scientific evidence to support these claims, many people find that the ambience created by these lamps does help them relax. As for Himalayan salt used in food, it contains about 84 minerals, including magnesium, potassium, and calcium. These minerals can help maintain balance in the body, improve digestion, and regulate fluid levels. Incorporating Himalayan salt into your diet may be a beneficial addition to a healthy lifestyle. Himalayan salt is also known for its therapeutic properties. Some people use it for salt baths, which help with relaxation and can improve skin condition. Additionally, it's used in salt inhalation therapy for respiratory issues. Its natural composition and lack of chemical additives make it a preferred choice for those focused on their health. Himalayan salt also has a milder, more complex flavor compared to regular table salt, making it popular among chefs and food enthusiasts. Imagine if every glass bottle you throw away could become the key to saving the planet, and even earn you some extra cash. Did you know that over 130 million tons of glass are recycled worldwide each year? I recently visited one of the largest recycling plants to uncover the fascinating secrets of how ordinary glass takes an incredible journey from the trash bin to new possibilities, transforming our lives along the way. So, how does a glass item get a new life? The recycling process for bottles begins with collecting used glass. In many cities and countries, a system of separate waste collection is in place, which greatly helps with efficient recycling. Special containers for glass collection are set up in various locations, separated from those for plastic, paper, and organic waste. This prevents glass from mixing with other materials, making the recycling process smoother. In some countries or companies, glass collection points have been established, where people can return used bottles and receive a reward in exchange. This encourages the public to participate in gathering and returning glass bottles for recycling. In many former Soviet Union countries, the collection of glass is often carried out by vulnerable and marginalized groups. However, in European Union countries, it is a routine practice for everyone to return used containers, often receiving something like a discount on their grocery bill in return. Once collected, the glass is sent to recycling plants, where the main processing begins. Once the glass bottles are collected from containers or drop-off points, they are transported to specialized sorting centers for further processing. Waste collection trucks periodically pick up the glass from these containers and deliver it either to sorting centers or directly to recycling plants. This is typically done on a large scale to make transportation more efficient. At the plants or sorting stations, the trucks unload the glass bottles into large containers, where they begin the preparation process for sorting and recycling. Once the bottles arrive at the facility, the next step begins, sorting the glass by type and color. This step is crucial to optimizing the recycling process. Sorting glass by color is extremely important because different glass colors are used for different products, and mixing them can reduce the quality of new items. The bottles are sorted automatically using special optical scanners that detect the glass color and sort it into clear, green, and brown categories. This is crucial since each type of glass requires separate recycling processes. These sorting machines are equipped with sensors that identify the color of the glass using light sensors. Whole bottles or glass fragments move along a conveyor belt, where machines illuminate them with a lamp or laser. The light reflected from the glass is analyzed by the sensors. The system identifies the glass color based on the signal received and sends this information to a controller. After identifying the color, each glass piece is directed to the appropriate section, either through a stream of air or mechanically removed from the conveyor. The glass is then separated into different streams, which significantly simplifies the next steps of melting and reuse in new products. Once sorted by color, the glass passes through magnets and air streams to remove metal elements like bottle caps, as well as other impurities such as paper labels or plastic residues. Powerful magnets are placed along the conveyor belt to capture all metallic impurities, including steel caps, while electromagnetic separators are used to remove aluminum caps and foil pieces. Pneumatic systems are used to blow away plastic and label remnants from the conveyor. using strong air currents to clear away any materials that are not needed for further recycling. Of course, the glass also undergoes a wet cleaning process in special washing systems, as many of these bottles will be reused to make containers for food products. Just think about it. We discard bottles without a second thought, not realizing how much effort goes into recycling them. Compared to other materials, glass does not wear out or degrade with use, making it an incredibly sustainable material for continuous recycling. After the sorting process, the glass is crushed into what's called cullet, which serves as the raw material for making new glass products. Specialized machines are used to break down glass bottles into small pieces, making further processing easier. These crushers come in various types, but most work using a mill with two parts, one stationary and one movable, where the glass is ground down as the two parts rub against each other. Crushers can include jaw, cone, roll, hammer, and gyratory types. The glass is fed into the crushing machine via a hopper or conveyor belt, and inside, mechanical elements reduce it to the desired size. Some crushers go through multiple stages of crushing to ensure uniform particle size. At this point, any remaining impurities that were not removed during sorting can be further filtered out. After crushing, the cullet is sifted to remove pieces that are either too large or too small. This is done to ensure a uniform mixture of cullet that's ready for melting. From this finely crushed cullet, new bottles and jars are most often produced. It can be a bit unsettling to think that something made from waste ends up as new tableware, right? But the powerful processing and extremely high temperatures used in recycling leave no chance for the glass to carry any trace of its former life into the finished product. After being crushed, the cullet undergoes further cleaning to remove any remaining contaminants and is treated before heading to the melting furnaces, starting with magnetic separation. This process eliminates any leftover metals that may have passed through the sorting phase. It's crucial because even small traces of metal can disrupt the glass melting process. Next, specialized technologies are used to remove any organic residues, such as paper labels, adhesives, or other materials, ensuring that the cullet is completely clean before melting begins. The glass fragments are then sent to vibrating sieve machines, where they pass through screens of various sizes to separate the cullet into different grades based on particle size. Different grain sizes are used for different glass products. At this stage, the entire process is automated, with machines equipped with monitoring and control systems. The use of specialized machinery also reduces the risk of injury for workers handling glass bottles, as the entire process takes place in a controlled and safe environment. After being cleaned, cullet is sent to recycling plants, where it is transformed into new molten glass. At the plant, the cullet is loaded into special furnaces, where it melts at temperatures ranging from 2,800 to 3,000 degrees Fahrenheit. The glass becomes liquid and ready to be shaped into new products. Adding cullet to the melting process reduces energy consumption, as recycled glass melts at a lower temperature than raw materials. Occasionally, new raw materials such as sand, soda ash, and limestone are added to the melting process to maintain the chemical composition and quality of the glass. This helps ensure the strength and clarity of the new products. Once the glass is transformed into a molten state, it is used to produce new glass items. The liquid glass is poured into molds to create various products such as new glass bottles, jars, vases, or other containers. Lower quality recycled glass is often used as filler in concrete, which enhances its aesthetic appeal, increases strength, and improves thermal insulation. In large factories, this process is fully automated and may involve high-precision molds to ensure the desired quality and thickness of the glass. After shaping, the glass products pass through specialized cooling systems, where the temperature is gradually reduced. This step is crucial to prevent cracking and ensure the mechanical strength of the finished products. After forming, the new glass products undergo rigorous quality control to ensure they meet safety and durability standards. Optical and mechanical tests are conducted for this purpose. Specialized systems inspect the products for defects such as air bubbles, cracks, or improper shapes. If a product does not meet the required standards, it is sent back for recycling. Additionally, the items are tested for mechanical strength, especially in the case of glass bottles, which must withstand pressure and other stresses during use. Once all stages are complete, the new glass products are packaged and transported to the market for further use. In large factories, the packaging process is also automated. Glass products are grouped and packed into cardboard boxes or placed on pallets for easy transportation. The finished goods are then shipped to warehouses or directly to customers, such as beverage, food, and other product manufacturers, where they will be used again, allowing the glass recycling cycle to start anew. This process is both economically and environmentally beneficial. Glass recycling plays a significant role in reducing greenhouse gas emissions and water pollutants. By using recycled glass material to produce jars and containers, we can minimize waste and lower our carbon footprint. Additionally, producing glass from raw materials requires extraction methods that negatively impact the environment, making recycling a much more sustainable choice. Glass recycling offers significant environmental benefits due to its energy efficiency. Using recycled glass, cullet, helps reduce energy consumption in the production of new products, as melting cullet requires lower temperatures than melting raw materials. Researchers in this field have noted that energy use can be reduced by 3%. Recycling also decreases the amount of waste sent to landfills. Since glass does not naturally decompose and can remain in the environment for thousands of years, recycling it is crucial for environmental preservation. Additionally, glass recycling conserves natural resources. By recycling glass, we reduce the need for raw materials like sand, soda ash, and limestone, helping to preserve these resources for future generations. Thousands of tons of Doritos are eaten around the world every year. Imagine giant harvesters gathering tons of corn to produce 70,000 bags of your favorite snack every single day. Want to find out how ordinary corn kernels turn into the crunchy triangles we all love? Then let's take a trip to the Frito-Lay factory and uncover the secrets behind making one of the world's most popular snacks. March West, the head of marketing at Frito-Lay, founded Doritos in the 1960s. He discovered crispy tortillas at a nearby restaurant in San Diego, California. The idea to cut corn tortillas into triangles, fry them, and season them came to him when he had leftover tortillas that couldn't be used because they were broken or didn't meet the standards for sale. The word Dorito comes from the Spanish word dorado, meaning little pieces of gold. Doritos became the best-selling chips in the world in 1988 and remain popular to this day, with 10 different flavors available. The main ingredient in Doritos is cornmeal, which sets them apart from regular potato chips. Corn cobs are carefully harvested from the plants. The cut has to be cleaned to avoid damaging the kernels and to keep the cob intact. Up to 140 tons of corn can be harvested in a single day, ensuring the factory has everything it needs. The stalks are cut just above the ground, then the cobs are removed and tossed into a container. Once the container is full, the large pile of corn is loaded onto a truck for processing. The supplier cleans and dries the corn kernels. The process involves passing them through a vibrating sieve to remove dust, as well as any stones or sand. The moisture level of the kernels then needs to be raised to 14%, which is critical for the next stage of production, where the corn is sent to the nacho factory. Every day, 99,000 pounds of corn are delivered to the factory. The dried corn is transferred from massive silos into a pot, where it is cooked in water. This amounts to over 14.3 million pounds of finished product per year. That's a lot of corn. Frito-Lay operates one of the largest chip-making factories in the world, producing more than 100,000 bags of nachos daily. The factory is divided into 4 main zones. In the corn zone, tortilla products like Doritos are made. At the center is a 700,000 square foot distribution center. About 70,000 bags of Doritos are produced per day, which adds up to roughly 18 million bags annually. A Upon arriving at the factory, the first thing you notice are the two corn storage silos, each holding 265,000 pounds. From this supply, the factory can produce 44,000 pounds of Doritos. To make Doritos, the corn must be cooked before being placed in the soaking tanks. First, it is boiled in large kettles with stirrers at near boiling temperatures. Then, the corn is transferred into 18 open tanks, where it is left to soak for about 12 hours. Each kettle holds around 660 pounds of corn and about 200 pounds of water. The corn is boiled for about 4 minutes at 200 degrees Fahrenheit, and then left to soak for 12 hours. After cooking, the corn is transferred into large tanks, where it soaks overnight to soften. The corn is left for 12 hours to absorb more water. The soaking process allows the corn to take in moisture and helps remove the hull, the outer shell of the kernels. A machine filters out the water, leaving only soft, hydrated corn. When the moisture content reaches 45% and the hulls are softened and loose, the corn is sent to a washing machine by a pumping system. The loose hulls are removed with a water spray. From the drum, the corn is carried on a conveyor belt to the milling machine. After being cleaned, it enters the grinder, where rotating millstones grind the corn into a dough. The kernels are literally crushed between two stones, resulting in a smooth corn paste. During the milling process, water is added to the cornmeal to create the right dough consistency. The dough is checked for 3 key factors: moisture content, temperature, and grind texture. It exits the mill through a small nozzle, forming a thin sheet. This dough sheet is placed between 2 metal rollers. A third roller is responsible for cutting the dough into individual triangular nachos. The dough sheet passes through rollers with triangle-shaped indents. First, it goes between the 2 rollers, then through a cutter that gives Doritos their signature shape, much like a cookie cutter. The sharp edges of the roller cut the dough into perfect triangular pieces. This machine can cut 6,000 chips per minute, producing over 8 million chips a day. The cut chips are placed on a conveyor belt that carries them to the next stage, the oven. Although the process is well designed, there's always some leftover dough, but it doesn't go to waste. It's sent right back to the dough vats to start the process all over again. Now it's time to cook those tortillas. The triangular chips are placed in an oven at 644 degrees Fahrenheit. However, this isn't just any oven. It has 3 temperature levels and reaches several hundred degrees. The nacho triangles spend only a few seconds in the oven to give them the right texture and prevent drying out, while sealing in moisture that creates the signature Doritos bubbles. The industrial oven seals the outer surface, locking in moisture, which causes the dough to puff up and form bubbles. This is what makes Doritos so crunchy. 16 seconds in the oven is enough to dry the dough just enough so it doesn't break when handled. The bumpy texture of Doritos is a result of the heat pulling small moisture bubbles to the surface of the dough. The tortillas are then cooled on several conveyor belts and sent to the fryer. This brief pause also allows inspectors to check that none of the tortillas burned in the oven. The triangles are fed into the fryer on a conveyor belt. The oil is heated to 360 degrees Fahrenheit, and the nachos are fried for 55 seconds. During this time, the nachos develop the perfect color and texture. The bubbles on a finished Dorito are air pockets formed during the frying process. They are then removed using a mesh conveyor belt. As they come out, the fryer is filled with leftover oil. Next, the Doritos are transferred using vibrating conveyors into a special drum, where they are mixed with the right seasonings and ingredients. At the next station, a screw conveyor feeds the nacho seasoning into the drum. Huge bags of the seasoning mix are added to the top of the machine, and a hopper containing the secret blend of cheddar cheese, Parmesan cheese, and spices is placed into the drum. Various cheeses, spices, flavor enhancers like monosodium glutamate, and preservatives are the key ingredients that extend the product's shelf life. To make the surface of the nachos stickier so the seasoning adheres, some nozzles coat the nachos with canola oil. Despite how intimidating the large drum might seem, it evenly distributes the seasoning. The delicate chips are handled in a way that prevents them from breaking apart while moving through the drum. To ensure they are fully cooled before packaging, the seasoned Doritos move along a 98-foot conveyor belt. Once the nachos exit the drum, they head to the packaging section. Through hoppers, they are directed to various packing machines. The highlight of technical choreography is the packaging device. Each machine has 14 bucket scales. The Doritos are positioned, then pass through a weighing machine where a series of scoops accurately measures the weight of each bag of Doritos. A trapdoor opens, releasing the nachos, and the machine forms a strip of aluminum and plastic into a bag once enough chips are ready for packaging. The nachos drop into the bag, which is sealed and cut using heat, as the bottom of the next bag closes. Nitrogen is pumped into the bag, which is then sealed airtight. This process prevents oxygen loss, keeping the Doritos fresh for an extended period, and creating an air cushion to prevent the chips from breaking. Each large bag of Doritos contains about 100 chips. An operator ensures that each box holds 8 bags. The plant's production and packaging output of 70,000 bags of Doritos per day adds up to more than 18 million bags per year.